Hello and welcome back. In our last video, I introduced the basics of what a microprocessor is and where it gets used. In this one, I am going to be talking specifically about the architecture of the 8086 and its various modes of operation. Basically, the first question that one should understand is, how do you define a processor? People talk about 8-bit, 16-bit, 32-bit processors. What exactly do they mean by this? And in this case, it really talks about the internals of the processor. How many bits does the register of a processor have? How many bits does it expose to the outside world in terms of the data bus? So on and so forth. So in the 8086, it's a 16-bit processor because it has 16 data lines that are exposed to the external world. All internal registers are 16 bits long too. And if you were to talk of a 32-bit processor, you would have the same thing, but 32 bits of internal registers and 32-bit data bus. In the case of the 8086, while the data bus is itself 16 bits long, the address is 20 bits wide. And therefore, you can actually address up to 1 megabyte of RAM or ROM as you will. 2 to the power 20 is 1 megabyte. Let's now look at the insides of this processor. There are two major chunks to this, two groups of functions that this processor performs. One is called the execution unit and the other one is called the bus interface unit. The execution unit really executes everything that you will for the processor. So it consists of the arithmetic logic unit, which performs the arithmetic and the logical operations required of any program. It consists of a set of registers that are necessary. They call the general purpose registers, including the accumulator. The beauty of this particular design for the 8086 is that the registers can be addressed either as an 8-bit register or as a 16-bit register. In the case of the 8-bit register, you have AL or AH, that is the accumulator low or the accumulator high. And if you wanted to address this as a 16-bit register, you would call it AX. So on and so forth for BX, CX and DX. All of these are general purpose registers used by the ALU to perform arithmetic and logical operations. If you now move to the bus interface unit, you first have a set of segment registers. These segment registers are used to address memory space, either ROM or RAM or the IO space by the processor. And there is an address compute engine within this which converts the logical address that is held by the segment registers into a physical address that is exposed to the outside world. Interestingly, there is a set of internal memory, if you will, that holds what's called the instruction queue, and we'll talk about this a little later. This is the insides of the processor. All of this together access the outside world either through an address bus, the data bus or the IO ports. Let's look at the bus interface unit in a little more detail. All right. So it handles all the data and addresses required by the processor to access the external world. Typically, bus instructions are fetching instructions, they are about reading or writing, so on and so forth. And the instructions are transferred to what's called the instruction queue. Now, we spoke about this 6 locations of memory inside the processor, which is used for holding 6 consecutive instructions. Why is this required? Really, the reason is that the processor, the execution unit of the processor is much faster than the peripheral devices like memory, ROM or RAM. In the earlier days, the memory was almost as fast as the processor, but from the 8086 family onwards, the processor became much faster than the external peripheral devices. And therefore, what the architects of the processor did was to build a queue inside the processor which permitted you to store in advance specific instructions that would be executed in the future. This whole concept is called pipelining. What you're really doing is filling a pipe full of instructions that the execution unit can access on the fly. And as and when an instruction is executed, the pipe gets filled by from the external memory automatically. Now, why does this help? the processor, the primary reason is the execution unit is then able to perform at optimum speed. And only when you need to do a jump instruction of some kind or the other does the pipe have to be refreshed completely, otherwise it's a sequential flow of instructions in the main program. Let's now focus on the segment registers. The segment registers are each 16 bits long, really performing specific operations and used for specific operations, and the segment registers of different kinds are used to calculate the addresses within the memory space of 1 megabyte. How is this done? Right? Let's look at this figure. This is the 1 megabyte memory space of the processor, 0000 hex to FFFF hex. This is the complete address space. Let's assume that the code segment register, the CS, points to 1234 hex. And then from there, because it's a 16-bit register, you can access 64 kilobytes of memory location. But 1234 hex is actually translated into 12340 hex by the address compute engine. So what really you are doing is shifting the value in the code segment register by 8 bits to the left, padding it with a 0 to calculate the physical address of the start of the code segment. The instruction pointer in this example points to 5678 hex is then added to this shifted code segment value to get the final physical address location of 179D8 hex. This is the way two 16-bit registers are used to calculate one 20-bit physical address, and this physical address is outputted onto A0 to A19, 20 bits long. The segment registers have various uses. The code segment register, for example, as the name implies, points to the code within the whole memory space. And you just simply by changing the value in the code segment register, you could switch across this complete 1 megabyte of memory anywhere you wanted, and as long as you really had RAM or ROM in that space, you could have different kinds of codes being executed at will. This map shows you the usage of 4 different segment registers. The data segment register is at the bottom, the code segment register is at the absolute top, you have the extra segment and the stack segment registers in between somewhere. You as the designer, you as the programmer are free to map this anywhere within that 1 megabyte space. The execution unit consists, as I said, of a bunch of general purpose registers. The AX register is the accumulator, and remember, the AX is the sum of AL and AH, each of which is an 8-bit register. And then you have the BX register, which is the memory pointer into the data segment. You have the CX register, which is a counter register, and as we go along you will understand the use of this counter register. You then have the DX register, which is used specifically for divide and multiplication operations. You then have 2 special registers called the index registers, which are the source index register and the destination index register, used specifically for string operations. On top of this, you have something called the pointer register. One is the base pointer value, and this is pointing to data within the stack segment. The other one is the stack pointer. So the stack pointer points to the top of stack, whereas the base pointer points to a location within the stack that contains data that the program wants to use. The last register is called the flag register, and it is used by the processor to maintain status and to interpret status of various assembly language instructions. The flag register is bit addressable, so each bit has a meaning. This is kind of in brief the architecture of the 8086. Let's look at the 2 modes of operation that the 8086 provides to you as a designer. It's called the minimum mode and the maximum mode. In the minimum mode, you cannot add any other co-processor to your design. It is called a single processor system. Whereas in the maximum mode, you are allowed to add additional co-processors like, for example, the 8087 arithmetic co-processor. In the minimum mode, the 8086 is responsible for generating all control signals on its own, and in the maximum mode you could use additional bus controllers to do this for you. In the minimum mode, you primarily use this in very simple applications, whereas in the maximum mode, where you have fairly complex applications, for example a personal computer that's based on the 8086, you would use the maximum mode. How do you decide whether the processor is acting in the minimum mode or the maximum mode? This is really defined by pin number 30 on the processor, and if you pulled pin number 30 high, that is to 5 volts, you enable the minimum mode. If you pulled it to ground, that is low, you enabled the maximum mode. Obviously, many of the pins have a common function across both modes, and by studying the pinout diagrams of the 8086, you will begin to appreciate what those pins are and where you would use them. So this brings us to the close of this section on the architecture of the 8086 and its modes of operation. In our next video, we are going to be looking at the example of how to read bus timing diagrams. What are bus timings, how to read them, and how to use them effectively when you are designing a system. Till then, I would urge you to read up a little bit more on the architecture of the 8086. Try and understand where you would use the minimum mode and the maximum mode. I have given you a few pointers. And of course, do read up on our next video, bus timing diagrams. Till then, thank you.